So in this lecture, we will means further investigate and explore the properties of our transition matrix. So what is transition matrix? It's very interesting things like but for our ready reference, I would like to write piano Becker series once again because I think you people have forgotten it because it's not a very nice looking one. But nowadays, many one are trying that fractional order differential equation. Although I am not very convinced with the use of that fractional order differential equation. It's look like when you can even score something in using a very orthodox cricketing shot, you are trying to do something very uncommon and means like unnecessary increasing the complexity of your own work. But still, as people are trying to try their luck on your fractional order control, so I think you people may find it a bit more helpful if you consider it. So it goes till like this. Now, one thing that this time varying things is pretty clumsy and not very convenient to means like convenient to be expressed in common forms, but still time varying system should be studied because most of the systems are in reality is time varying in nature. The days during which we were or we used to model our system by means of time invariant systems are gone. Nowadays, obviously, if you go to means age old industry, still they are happy with PID. So uh, I'm not actually arguing for anything, but my point is that one must means upgrade himself to undertake the case of time varying systems. Now, for time varying system, obviously I'll discuss a separate session on time invariant, but let us discuss two special cases of time varying system. So, let us consider that now what happen in case of time invariant system if we have right. So then your this piano Becker series that will boil down to what? That will boil down to this kind of thing like a term in your piano Becker series will become this one. Because all the A will become invariant of your integration. So it will be if you want you can verify this result of this integration. Now uh, the property, like, let us discuss a few properties interesting. And one more request, that when you share a video, please share the screenshot of that video. Right? And here this matrix exponential can further be expressed like EAT is equal to uh, obviously this converges uniformly and absolutely in a bounded interval is arbitrary. So this bounded interval, obviously, here I would like to mention one thing, that whenever you consider something is infinitely large, as we do not know what is in, means the point infinity, where does it lie, you cannot write something like this. You have to write it like this. That means here you are having something that is tending to infinity, but it's not equal to infinity, right? It is very close to infinity, so that is why you can't write it like this. Okay, so please keep this in your mind. uh, Now we would like to prove it, that so how we can prove that for any finite arbitrary bounded interval, the matrix function that I have shown you, that is EAT, is bounded. So within this interval, what we can write, we can take the norm of this spectral norm. Now see this tk, what it could be, the maximum one, it will become now. Therefore we can write because we can write it, because All these are bounded. Now if we apply Weierstrass M test, here to prove this one, you can easily find it. You will see that this series right. Now try to understand one more thing, that within a finite within any finite time interval, EAT is analytic in nature. I hope you have studied the theory of analytic function in your Nyquist. So it's analytic. Therefore, now think about what would happen to the zero input solution of a time invariant system. For zero input, your second term will vanish, only your state response will be there, like initial state will be manipulated by your state transition matrix, or state transition matrix will act upon on your initial state. So what we can write, a very important line, see here we have intentionally uh, means putting stress or emphasis on finite time interval. We do not know what would happen if the interval is infinitely large. So there comes the concept of stable unstable system that we'll discuss later, while the asymptotically stable system will converge, the means unstable system response will diverge. But even if you consider a finite interval, you will find their response is means try to be a bit more intuitive and means imaginative, so that you can visualize this what is happening there. Like you are having a matrix, say let me, if you are not able to visualize it, let me help you. Suppose your, let us take an example of 2 cross 2 initial condition. You are having a matrix sorry A is in diagonal form. So what would happen to AT? It will become e to the power 2t. So what would happen to your xt? Your xt will be basically right. So if this is your xt, then think about this, that what about the means system, if you try to plot, you need to plot two curves. One is t x1t, another one is x2t. What you will see that tx1t, say at 10, it will grow with a factor of e to t, right? But still, what is happening once is, until you are sorry, this is not the case. Probably exponentially rising curve must be like this. Now what you will observe, that as long as you are taking a finite interval, this will never give you something means infinite large value. Only infinite things you will get when it is like the interval itself is infinite. Now let us consider the second property, that is for actually here we are trying to exploit something that is you can say it's means the product is commutative in nature. If this relation holds good, then it implies right. So let us number it. Let it be equation number 3 and this be 4. So if 3 holds good, then 4 will be true. So we need to prove this property. How we can prove? See, I think I have shown you it somewhere. We have done so many things, but so many useless things that now I am not getting. Just a minute. Well, so last means here this is equation number 4. Now I have already solved this example in my last video or last video. There you must be able to see that for this kind of diagonal structure, what we can have like the kth term of our diagonal matrix phi will be like this. So here this one like the one which I have shown here is like, we'll take this kind of shape, right? So like means this is what we are going to exploit here. Now for sake of means saving some time, what I would like to do here is that to directly go means I have written a few steps. Like from that example we can write this, right? This is a straightforward that I have already marked here. Now let us use this identity in a means kind of recursive manner on a general term of piano-Becker series from right, where you will have j is equal to means 1. So from that way let us start. So what we are doing here is that at first here we take means we have taken the highest and the second highest term. For kth term, this is the highest means in that sense sigma k and sigma k minus 1. We group them together. Then what we do? We have found out that if sigma k and sigma k minus 1 both are equal, then this whole integration can be punched up, or means can be means simplified in this way. So then again, after further processing, if we keep on doing the same thing, we are actually going to get something that is like one it is like 1 upon k factorial your right. Now this is corresponding to that exponential equation, that is what we saw here. This is equation 4. Now let us number them for our ready reference. Let this be equation number 5 and the final realization be equation number 6. Okay, so that now our task is to show that this holds at t is equal to means for any initial condition, but actually before we proceed, what we should means, if you are not very comfortable with chain rule, I suggest that you go to your undergraduate engineering maths book, whatever book you prefer, and just quickly means revise the concept of chain rule and also the product rule and Leibniz rule for differentiation. Here one thing I would like to mention, that chain rule calculation is not generally applicable to matrix calculus, because that is something depends on commutativity, but product rule and Leibniz rule for differentiation are always valid, because whenever you are trying to do differentiation of matrix, it is actually not in matrix form, rather you are trying to do element wise differentiation. So what we can write is that if you differentiate this left side of this one, like this term, let me try to select it from here only. This is the only advantage of using this whiteboard. Otherwise, everything is disadvantage. Now, if we try to do a differentiation of this whole thing, then what you will get? Fine. Now let us try to differentiate the right side. So what you will get here, this will become very interesting. It will be, let us go to next page. Here I cannot accommodate this whole thing. It's a big equation. Let me just write it carefully. So upon differentiating the right side, what we are getting, that is very interesting result. Like means we are using this like that condition of this one, like we are means if this holds, then we are actually trying to repeatedly means utilize this one here, and oh God. So now we use this, and what we get is that is very interesting things. Here you can see that it is giving us what? We are getting this means like term-wise differentiation we are considering. It will give you what? It will give you kind of things that is like yeah, yes, now this correct. So what it will result? It will result you like means that if you keep on differentiating, you will get this kind of things, and eventually it will result you something that is this. So we use that identity to reach this stage. So hence we have proved what we were means asked to prove. And one more thing, like for your n is equal to 1, it will become a ordinary first order differential equation, and that is will become very common that your transition, it will become, instead of transition matrix, AT will become a kind of transition scalar. It will be in that case okay. Now let us go to some general properties. T, that is final time, tau or T naught initial time, and sigma and intermediate time, we can write that the transition matrix for AT so let us select arbitrary fixed value for tau and sigma. What we can write that RT, let us define RT is equal to what is here in this side. Now if you do this, of R yields what? If you do it, what you will get? You will get something like this. And of course, if you do this, it should result you this is true for all t. Right. So the initial condition is you can say that initial condition at t is equal to sigma. If you set t is equal to sigma, then like here, then both of these are becoming the same thing. Why so? Because if you set t is equal to sigma, this part will result to what? What we know that when we equate the two argument, like you do not need to transit. If you put or if you allow passing up to same argument through phi, this is a function that will produce an identity matrix. That means it will imply you do not need to proceed anywhere. Wherever you are very okay, very good, you stay there. So this will be true, like if you see, then this RT will also become we can write R sigma is equal to then by uniqueness of solution of your matrix, because we proved that solution is unique, we can say that therefore it is clearly means like if this is true, then just putting t over here will also means yield us the same thing, because this argument works for every value of tau and sigma, right? Now, the approach we utilize here to prove is a kind of extension of the approach in the proof of our that previous one, that is here. This one. So try to find out the similarity between these two proofs and let me know. I'm just giving you the hints that they are very similar in some way, but you please try to figure it out. Now, if you want for graphical interpretation, we can prove it using a few fixed values like T2, T1 and T0. So we can write xt2 is equal to so what we are looking for proving something like but indeed this one is also is equal to so clearly you can see that if you replace x1 by this, then you will get this property. So graphical interpretation would be something like this. Your t is here. Let us consider only variation of single variable xt. Here it is your xt naught. Now here it is your x1t and here it is your x2t. So how we have reached this x1t, that is this trajectory was governed by now if you see Actually, these two are overlapping trajectory due to my drawing means just slightly drawing problem. It becomes something like this. Let me. It is the same trajectory. If any deviation takes place, that is due to my poor drawing. So this whole thing is what? Then what another you can have? You can have from here to here. But you will reach the same position. Now let me ask you one question and think about it. Like if we exchange the position, like just to alter the position, like can it possible for us to reach x1t from x2t? Or means sorry, I made a mistake. It is not xt1 and this should be xt2. Yes. So is it possible to reach xt1 from xt2 where t2 is less than means t2 is greater than t1 just by doing the same thing and exchanging t1 t2. Forget about that, means keep the idea of causal system aside. Just think about it, that can we reach the same initial point if we follow or if we try to find out some kind of reverse trajectory? Think about it. Oh, I think there is some space, yeah. Now what is next, that for every t and tau, the matrix AT satisfies determinant of phi t comma tau is equal to, this is very interesting and important property. So the key is to show that for any fixed tau, our scalar function, this one, is like means d dt of determinant of this. If we can prove this one, So can we apply chain rule here? If tau is fixed, we can use chain rule with the following notation, like Cij t comma tau be the cofactor of the entry and denote the I comma jth entry of the transposed of the original cofactor matrix. Right? Now let this cofactor matrix be if cofactor matrix is this one, then what we are trying to say is that now see, if you see this determinant, try to understand that you can visualize determinant as a like for a matrix with continuous entries. Its determinant will also become that is very interesting. One property I would like to mention here, that any continuous function on a closed subspace, its image will also form a closed subspace. What I am trying to say, that suppose if you take this, if you take something, say if we take a range, in this range you will see that sin t is continuous and its corresponding one will form this. So what we can say, that if it is a continuous function over a closed interval, then its image will form a closed interval. Actually it is people used to say it in reverse way, like if the image of a function is closed interval, then it is actually its domain is also a closed interval. Now we will try to means apply this concept here to realize that our determinant is differentiable function. So if determinant is differentiable, then we can we can use the chain rule to figure out that d dt of will give us what? Okay, so if you do this computation